how much does it cost to get from one place to another? Well, to get a bus to the shop, you might need $10. To get a short flight to another city, you might need $100. And to fly across the world, you might need $500. But what about a trip into space? Well, for this, you'll need a lot of delta V. Delta V is a total boost in velocity or speed that you need to reach a certain part of space. The further you want to go, the more delta V you'll need. For example, launching from the ground to a low Earth orbit will cost about 9.3 kilometers per second of delta V. Going from the Earth to the Moon will cost about 13.3 kilometers per second. And going from the Earth to Mars will cost about 14.5 kilometers per second. Now, each rocket will have its own delta V budget, and generally speaking, the larger the rocket, the more delta V that it has to spend. To work out a rocket's delta V budget, we use the rocket equation, which looks like this. A rocket's delta V is equal to its exhaust velocity times the natural logarithm of its final mass after it's burnt all of its fuel, divided by its initial mass before it's burnt all of its fuel. How do we come up with this equation? Well, it's through solving a differential equation. First, we form our differential equation. Imagine a rocket moving through space with mass m and velocity u. Its total momentum is simply its mass times its velocity. But imagine that this rocket very briefly turns on its engines. It releases a very small amount of propellant with mass dm. The velocity of that propellant is the ship's velocity minus the exhaust velocity. Because the ship has released some propellant, its total mass is now m minus dm, the released mass, and the ship has gained a small amount of velocity, u plus du. The total momentum after the rocket ignition is now the momentum of the rocket plus the momentum of the released propellant. We then apply one of the most fundamental principles in physics, conservation of momentum. The momentum before the rocket turns its engine on and releases the propellant must be the same as after. Subbing in both our expressions for momentum, we can then expand the brackets on the right side. We then cancel out like terms, and the dm du we can cancel too, because by definition it's infinitesimally small, and after rearranging we're left with the differential equation mdu is equal to vx dm. The first step of solving our differential equation is to split our variables. We simply divide by m to get du equals vx over m dm, and we're assuming that vx, the exhaust velocity, is constant. In step 2, we then integrate both sides. The left side, we can integrate between the ship's final and initial velocity, and on the right, we remove the constant vx, and we integrate 1 over m between the ship's final mass and its initial mass. This gives us vf minus vi equals vx times ln mf minus ln mi. We then find our general solution. Our final velocity minus our initial velocity is simply our delta v, and we can also tidy up the right hand side. And there we have the rocket equation in its full glory. So how do we use it? Well, in step 4 we can find a particular solution by finding the delta v of a particular rocket. Let's take for example Starship, the newest creation of Elon Musk's SpaceX. The exhaust velocity in the equation can be replaced with ISP, the specific impulse, times the strength of gravity at sea level. ISP is basically like the miles per gallon for a car. The higher it is, the more boost that you get for a certain amount of fuel. We can also replace the final mass of the rocket with the rocket's dry mass, the mass without propellant, plus the mass of the payload, the thing that you're trying to take into space, and the initial mass is the same but also includes the mass of fuel or propellant. Starship uses Raptor engines with an ISP of about 325 seconds, G0 is minus 9.81 meters per second squared, the dry mass of the rocket is about 85 tons, the mass of fuel or propellant is about 1,285 tons, and let's assume that we have a payload of about 100 tons. We're taking 100 tons into space. Plugging in the numbers, we get a delta V budget of about 6.6 kilometers per second. What could we do with that? Well, let's imagine Starship is fully fueled and is in low Earth orbit. Well, a transfer orbit to Mars costs about 3.6 kilometers per second of delta V, and an orbital insertion to low Mars orbit would cost another 1.4 kilometers per second. But to get back home costs about 2.1 kilometers per second. Sadly, Starship only has about 1.6 kilometers per second left in its delta V budget. It doesn't have enough to get home. How sad. Thank you for watching. Please like and subscribe for more maths lessons and worked examples.